Right, so continuing on with, reviewing for this third midterm. So the third thing that's going to be tested is confidence intervals. So confidence intervals, confidence intervals, confidence intervals. Now, confidence intervals are pretty much all the same. So let's start with what's the same about them, not what's different about them. So if we're testing for means, so if we want to do, not testing, if we're finding confidence intervals for means, then we're going to use our X bar in order to estimate our population mean. So that is the big kicker here. That's what we want. We want to use X bar to estimate the mean. We don't know what the population mean is. If we're making an estimate for it, all we have is some sample data to tell us potentially what it may look like. So if we're doing that, then we can know one of two things, right? We have X bars and we may know sigma, right? Sigma is known. What that is the population standard deviation. You are told it's population standard deviation, or you're told that it's the variance for all possible points, right? All data. So that's how you know it's a population one. Just because you're told a sample and then you're given mean and standard deviation, you can't assume that it is the population mean. You have to know it as truly the population mean. So the other choice is that you have the standard deviation of the sample known. So sometimes you might not be told that straight out, you might have to compute it. But the big deal is sigma is not being told to you. Sigma is unknown. Now, each of these two things lead to different types of distributions for the X bars. So in order to calculate a confidence interval, we have to come back to the theory behind that. And that's based upon the distribution of the sample statistic that is used to estimate the population parameter that we're interested in. So what we need this to know is twofold. So these things are used, right, to know, and in terms of our confidence interval, it's going to be the first one. Or used to know in terms of our confidence interval. One of the things it's going to tell us is our critical value. Okay, so it's used to tell us what is the critical value that we're going to use in that margin of error computation. So critical value for the E computation. And then the second thing that this will tell us is what standard error to use in E. So remember, standard error is based upon the sampling distribution for the X bars, and standard error is the standard deviation that we have, sigma or s, divided by the square root of n. So that's going to tell us whether I use this for standard error or whether I use this for standard error. So sigma divided by the square root of n versus s divided by the square root of n. Okay, so that's for the why we have to know how they're distributed with the sigma or whether they're used with the s. Now, if we're dealing with proportions, they're also normally distributed, right? So if I have proportions, they're normally distributed. And we're going to be using the p hat to estimate the p in that case. So let's write that down. We're using p hat to tell us about p. And p hat, remember, that's x divided by n. It's the number of successes in our sample of n. So this is number of successes, remember. And that's in your sample of number. And so we're using the p-hats to estimate the p's. Okay, it's really super important. Let me write this in red. You do not, okay, do not use mu is equal to n times p here, and sigma is equal to the square root of npq. I cannot stress this enough, okay? This is a no. You don't use these things. No, definitely not. That is only for one single observation. This is a sample of size. These p-hats are distributed normally according to very much like our central limit theorem. So let me write down here our p-hats. The p-hats are distributed normally with a sample proportion that is supposedly equal to the population proportion here, and the standard deviation, or the standard error, of p times q divided by n. That's how these things are distributed, not with these. They are not the same thing. This is for one single, this is for multiple. Central limit theorem idea there. And that's one of the major issues with students in seeing this, is that they think that they're a little bit different. And this is going to tell us, number one, that we're going to use a critical value. That's a z, right? That's the normal part of it. And so when we do proportions, the sampling distribution of the p-hats is normal, so we use a z for a critical value. And second of all, it's going to tell us that our standard error that we use, the standard error is going to look like the square root of p, and we're going to use p-hat because we don't know what p actually is, right? We're trying to estimate it, so we use p-hat and q-hat. And it's the fact that we use p-hat and q-hat here when it really should be p and q that we can't use a confidence interval to give us a statistically significant hypothesis test in doing hypothesis testing via confidence intervals. And that's why you don't do hypothesis tests using confidence intervals for proportions. So now, with that said, let's talk about how all of these confidence intervals are similar. So confidence intervals, wow, well, this one actually works quite well, this page. A confidence interval for an estimate of mu when sigma is known is going to be based upon the normal distribution, right? And it's going to look like mu is mu is equal to x bar minus the margin of error and plus the margin of error. And that's what your confidence interval's margin of error looks like. It's the z-score times the standard deviation of the population divided by the square root of n. If I'm estimating for the population standard deviation, oops, I don't have one here. If I'm estimating for the population mean and I don't know the standard deviation, here's what changes, right? It changes to a t here and it changes to s here, right? That's what the change is. This doesn't change. This changes here and here, and you see it's the same place it was there. Now if I go and I do this for proportions, so let me erase this and say, okay, now I'm not talking about a mean anymore. I'm talking about a proportion now. Well, if I'm talking about a proportion, then I have my p-hats. That's my sample statistic that I'm using to estimate. Those are distributed normally with a mean that's equal to theoretically to the population proportion and divided by, and this is where we have the p-hat, q-hat divided by the n. That's our standard error. And this down here, it's going to go back to the z, right? Because that's how these things are distributed. They're distributed normally. And instead of looking like this, this is where I put in the square root of my standard error, right? The p-hat, q-hat divided by n. And so that's how these things are similar. And the differences really rely upon the sampling distribution of the sample statistic that we're using to estimate our population parameter. So that's what you need to understand. So I'm going to write that out in yet one more different way here. So I'm going to say all T and Z, okay, confidence intervals, they all look like whatever our point estimate is going to look like, plus or minus a margin of error. Always, that's what they look like. And if we have a p-hat to estimate the p's, and we have x-bars to estimate the means. And this one is whether we're using a standard deviation known or unknown, right? We're still using x-bars to estimate those things. So our margin of error is what looks slightly different. This is a z divided by, or multiplied by sigma and divided by a square root of n for a mu, and that's when sigma is known, right? It looks like a t with an s and a square root of n when we're estimating for mu again. But all we know is s. And finally, it looks like a z with the square root of p hat q hat over the square root of n when we're estimating for p hat. So you see these all look similar. They all look like my point estimate, and my point estimate is either p hat or x bar, right? So we've got to p hat or we've got to x bar. Those are our point estimates. So point estimate plus or minus the margin of error, and these are what our three margin of errors are going to look like. So I'm going to now talk about the variance, which is the last thing that I cover. So a variance, I can't erase that. The variance that I need, the variance estimate, so estimating a population variance, this is not based on a symmetric interval. This is a non-symmetric interval because it's not based upon a t or a z distribution. It's based upon a distribution called a chi-squared. So the thing that we need to understand here is that this is not symmetric. It is a skewed distribution, which is basically not going to give us one of these. So we don't have s squared plus or minus some margin of error. That is not going to cut it for us. No, 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 that is not the case. So what we want to do is we want to realize that this is based upon this distribution called a chi-squared distribution. This is not something squared. This is its name. It is a chi-squared. Okay, so you don't square anything in a chi-squared distribution. That's just its name. So don't think you're going to get a value and then square it. So just get that out of our head. And the confidence interval for this, it looks like these degrees of freedom times the sample variance divided by a chi-squared right value, and then that's less than the variance of the population, which is less than the n minus 1 times s squared. Notice the same thing here as this over there. And then it gets divided by a chi-squared left value. Now this interval is non-symmetric, and that's what we have to understand. This is how we calculate it. And it's because the distribution, the sampling distribution of these s squared values is a chi-squared distribution. So now I'm going to go ahead and pause this or go ahead and stop this video. I'll come back with one last one to finish up everything that we need to talk about.